Good afternoon, dear friends. Today we'll start the chapter 7, rules of differentiation and their use in comparative statics. We are kind of starting to apply the things we are learning, the differentiation, their rules, and their application in comparative statics, the comparative static analysis. And we are approaching the midterm exams as well. So, first we will deal with the rules of differentiation for a function of one variable, and then we will apply the rules for multivariate functions as well. For the moment, we will be dealing with functions of one variable only. The constant function rule is the simplest one. When we have a function y equals f of x equals k, a constant k being a real number, a real constant, then its derivative dy over dx is equal to 0, or dk over dx is equal to 0, or f prime of x is equal to 0. Those are the ways to express the same thing, which means the derivative of this function, the constant function, is 0. And it is quite intuitive because a constant means something which doesn't change, and the derivative is the rate of change in limit, the limit of the rate of change. As the derivative of something which doesn't change is bound to be 0. The change of something which doesn't change is bound to be 0, isn't it? So we can express the same thing as dy over dx, or dfx over dx, or dk over dx. All these are the same thing, and they would be equal to 0 naturally. Let's prove it, and then let's see more intricate rules. The proof goes like this: f of x equals k, so f of a given value n would be equal to k as well. It's a constant function for all n in real numbers, for all n being a real number. So the derivative of this function at the point n, f prime of n, by definition is equal to limit when x goes to n of f of x minus f of n over x minus n. So replacing f of x and f of n by its value in this function, which is k in both cases, we obtain limit when x goes to n of k minus k over x minus n. The denominator is the same, x minus n. And x goes to n does not mean that x is equal to n. On the contrary, it means x approaches n very much, but it never touches it. So x is never equal to n, so that x minus n never becomes 0. It approaches 0 very much, but it never becomes 0. But k minus k is 0. So the numerator is 0, the denominator is something which is not 0, although very small. Thus, we have 0 divided by something which is not 0. So it is 0. And its limit when x goes to n of 0 is 0, naturally, isn't it? So, and we have to generalize this as well. In our book, the authors are a little bit sloppy in generalizing the result, but we have to generalize it to all x's, all real x's. So, the generalization goes like this: no constraint is put on n. Thus, this result is valid for all real n numbers, n values. That's to say, for all x belonging to R, f prime of x is equal to 0. The derivative of x is equal to 0. And note that the derivative of a function for all x's is equal to 0, and the derivative of a function at the given x0, a given value x0 equals 0, are not the same thing. The derivative of a function is always 0, everywhere 0, if and only if this function is a constant function. But the derivative of any function can be 0 at some point, some given point x0 by chance. So those are not the same thing. Economic example would be a fixed cost function. The fixed cost function CF, it is denoted by CF here, is a function of the quantity produced or quantity sold, f of q, which is equal to 1,200 in this case, $1,200 for instance. Is it important? Of course it is important, because if the cost of the fixed cost of doing something is high, then it may hinder us from entering this market. So fixed costs are important. So the derivative of this fixed cost is the derivative of 1,200, which is 0. So the marginal cost of the fixed cost, marginal fixed cost if you wish, is 0. F prime of q is equal to 0. Why? Because it is constant. The derivative of something which doesn't change, the change of something which doesn't change, is 0. So the derivative of the fixed cost is 0, you see. Alright, when small n is equal to 2, 3, etc., how do we make it? For the moment, let's see. So this is the constant function. When n is, for instance, 2, then the why don't we have the case where we have n, just small n, which is interesting. Anyway, all right, perhaps we will see it afterwards, or anyway. So when n is greater than 2, how shall we find the derivative of it? First, let's observe something. X square minus n square over x minus n is equal to x plus n. Probably you know the property a square minus b square is equal to a minus b times a plus b. This is a property. This is always equal. This is always valid. It's always true. So if we have x square minus n square divided by x minus n, it is equal to x plus n, because x square minus n square is always equal to x minus n times x plus n. And if we divide both sides by x minus n, we obtain x square minus n square over x minus n is equal to x plus n. Similarly, x to the power 3, which is x cube, minus n cube, big case n cube, over x minus n is equal to x square plus nx plus n square. 3 terms on the right hand side. And if you don't believe, it's very easy to check. If you multiply x by x square, you obtain x to the power 3. Then when you multiply minus n by x square, it is minus n times x square. And then when you multiply this x with this plus nx, you obtain plus nx square. Minus nx square and plus nx square, they cancel each other. So when you continue multiplying like this, all the terms in between will cancel each other, and you will be left with x to the power 3 minus n to the power 3. You see, minus n times n square is minus n to the power 3. All the interim terms would cancel each other. 1 plus, 1 minus, and then they will cancel each other. So the general formula goes like this. X to the power small n, small cap n, minus big case n to the power small case n over x minus big case n is equal to x to the power small case n minus 1 plus n times big case n times x to the power small case n minus 2 plus n squared times x to the power n minus 3, etc. It goes on like this, and at the end you end up with big case n to the power small case n minus 1, and we obtain small case n terms on the right hand side. So this is an observation. We will use this observation for proving the general result. So what is the general result? Let's see it. F prime of n, which is the derivative of a function at the of course we speak of the rule f prime of x when x is when the function is x to the power small case n. Its derivative is n times x to the power n minus 1. This is the general result. So we will be proving this result. This is called the power function rule. I wonder whether we can... Oh yeah, I think here there is I think there has been a change in the order of the slides. That's why. So we should be going like this. We should be going like this, I guess. All right. Yeah. So definitely there has been a change in the order of the slides. We should have started with this one. The power function rule says when y equals f of x is equal to the x to the power n, small case n, its derivative is n times x to the power n minus 1, small case n times x to the power small case n minus 1. Or you can also say f prime of x is equal to n to the, times x to the power n minus 1. You just take the power in front of the x and you subtract 1. You take 1 less than the power. So this is the rule. For it's very easy to apply. It's a very general rule indeed. When we apply it, for instance, here with an example, when y is equal to x to the power 3, its derivative dy over dx, or dx to the power 3 over dx, is 3 times x squared. When y is equal to x to the power 9, its derivative is 9 times x to the power 8. Very easy to use, very easy to take the derivative. But we will prove it, of course. All right. For small case n equals 1, f of x is equal to small case n case x to the power 1, which is x. When n is equal to 1, the function reduces to f of x equals x. All right. So, and which means its derivative is I just take 1, the power 1, in front of the x and reduce it by 1, which is x to the power 0. X to the power 0 is 1, so 1 times 1 is 1. You see, the application is easy. But then we have to prove it. So, for any n in the real number space, in the set of real numbers, we can write down the derivative of this function at the point n, big case n, equals limit when x goes to big case n of f of x minus f of n over x minus n. And replacing f of x by its value at the point n, big case n, isn't it? Or x, and f of n, its value, the value of the function. What is the function itself? F of x equals x. So f of n is f of x equals x, and f of n is equal to n. So instead of f of x, we put x. Instead of f of n, we put n, big case n. So what we obtain at the numerator, x minus n. And what is at the denominator? X minus n. So this limit is equal to limit of x minus n over x minus n when x goes to n, big case n. But then x goes to n does not mean that x is equal to n. It approaches very much n, but never touches, never gets equal to n. So that x minus n does never get equal to 0. So if x minus n is not equal to 0, I can simplify x minus n at the numerator with the 1 at the denominator for obtaining 1. So limit of 1 when x goes to n is 1. You see that the derivative of f of x equals x at the point n is equal to 1. And we can generalize this result. No constraint is put on n. Thus, this result is valid for all real n values. That's to say, for all x's in the real space, in the set of real numbers. So f prime of x is equal to 1, as we claimed. So this is the proof. All right. For the general result, we should see the case where n is equal to 2, 3, and so on. And we have made an observation here. This observation, these openings, we will use them to prove the general result. So the proof is the same as the case of the power 1. But now the power is small n, any small n from 2 to whatever. So f prime of n, when the function is x to the power small case n, as we can see here, you see x to the power small case n. We will prove this result. The claim is that when y is equal to fx equals x to the power small case n, its derivative is small case n times x to the power small case n minus 1. We will be proving this result. All right, so let's prove it. So f prime of n by definition is equal to limit when x goes to big case n of f of x minus f of n over x minus n. This is the definition. F of x is x small case x to the power small case n, x to the power small case n, and f of big case n is big case n to the power small case n. So we obtain x to the power n minus n to the power n. And at the denominator we have x minus big case n. Great. And we take its limit when x goes to n. Very well. So what is the opening of x to the power small case n minus big case n to the power small case n over x minus n? We know from above that it is equal to this polynomial, x to the power small case n minus 1 plus big case n times x to the power x n minus 2, etc. up to big case n times n to the power small case n minus 1. Great. If we replace this expression with the right-hand side expression, this polynomial, which is equal, we obtain limit when x goes to big case n of x to the power small case n minus 1 plus big case n times x to the power small case n minus 2, etc. And at the end, big case n plus big case n to the power small case n minus 1, the same expression. And what is its limit? We know that the limit of a sum is the sum of the limits of the adding terms. So using this theorem, it's a theorem, the sum limit theorem. The limit of a sum is the sum of the limits of the particular terms making this sum. So we just distribute the limit inside the parentheses, like limit when x goes to n of x to the power small case n minus 1 plus limit x goes to n to of big case n times x to the power small case n minus 2, etc. And at the end, limit x to the power n big case n times big case n to the power small case n minus 1. And we add them up. But note, what is the limit of x to the power small case n minus 1 when x goes to big case n, it is big case n to the power small case n minus 1. And what is limit of big case n times x to the power small case n minus 2 when x goes to big case n? When we replace big case n here, we obtain big case n to the power small case n minus 2 and times big case n to the power 1. When in a multiplication with the same basis, the powers are summed up. So here there is 1, here there is n minus 2, n minus 2 plus 1 is n minus 1, small case n minus 1. So here we obtain big case n to the power n minus 1. The same for all the other ones up to here, and here it is a constant, big case n to the power n minus 1. Great. So we obtain all these terms equal to big case n to the power small case n minus 1. How many of these do we have in hand? Small case n times. You see? Here we have n minus 1 to 1 and 1. This one is, you can take it as x to the power 0 times big case n to the power n minus 1. So we have small case n terms here. So we have n times small case n times big case n to the power small case n minus 1. You see, we obtained the same expression. But we have to generalize. No constraint is put on the big case n, thus this result is valid for all real n values. That's to say, for all real x's, f prime of x is equal to small case n times x to the power small case n minus 1. That was what we had to prove. We have proven. Great. So let's see some examples how we use this formula. For finding the derivative of y equals x to the power 0. X to the power 0 is 1. What is the derivative of 1? It is simple. Just put the 0 in front of x and reduce the power by 1. So we obtain 0 times x to the power minus 1. As long as x is not equal to 0, this is 0. 0 times anything is 0. So if y is equal to x to the power 0, its derivative is 0. If y is equal to 1, its derivative is 0. Well, we can apply this formula for expressions which are not integers or which are not only polynomials, but other expressions which can be expressed as powers as well. For instance, here, find the derivative of y equals 1 over x to the power 3. Can we write down 1 over x to the power 3 as a power? Yes, it is x to the power minus 3 indeed. 1 over x to the power 3 is x to the power minus 3. So, if we take the derivative of this with the same rule, can we? Yes, we can. We just put the minus 3 in front of the x and we reduce its power by 1. Minus 3 minus 1 is minus 4. So we obtain minus 3 times x to the power minus 4. And which is minus 3 over x to the power 4, if you wish. You see? Very easy. If we want to find the derivative of y equals square root of x. Well, what is square root of x? It is x to the power 1/2. We have also proven it before when we were dealing with the powers. So we know that square root of x is equal to x to the power 1/2. So can we take the derivative of this expression with this formula which we have proven? Yes, of course. Just put 1/2 in front of x and reduce it by 1. Reduce the power by 1. 1/2 minus 1 is minus 1/2. So we obtain 1/2 times x to the power minus 1/2. Or 1 over 2 times x to the power 1/2, which is 1 over 2 times square root of x. You see? Perhaps you recognize this formula already. You have learned something somewhere perhaps. So it comes from there. If you can express any function as a power, as the power of x for instance, then you can take its derivative very easily using this formula. It's a general formula. Alright. If y is equal to x to the power 3. Very easy. Its derivative is 3 times x to the power 2, which is 3 times x squared, or f prime of x is equal to 3 times x squared. But this is the general derivative. Then if we want its particular value in some value of x0, for 1 for instance, then we first take the derivative and then replace the specific value. Here there is a note, but as you know, these frames, they shift a little bit when the presentation is transferred to this program. So here there is this note. It says first take the derivative as a formula and then replace the particular value, not the inverse. So when f prime of x is 3 times x squared, if I wonder what its value is at the point x equals 1, then I replace this x by 1. 3 times 1 square, 1 square is 1, 3 times 1 is 3. If I want to know its value at x equals 2, then I replace 2 instead of x. I obtain 3 times 2 to the power 2. 2 square is 4, 3 times 4 is 12, you see. So dy over dx when x is equal to 1. In fact, in mathematics, we use this expression as well. Any formula, any operator, or any expression, and if we put a vertical line, a long vertical line, and here we write a condition, it means we make this operation under this condition. So we first take the derivative theoretically, and then we replace the particular points. dy over dx when x is equal to 1, it is equal to 3. dy over dx when x is equal to 2, it is equal to 12. You see? Always make whatever you make. Theoretically, in general, and then replace the particular values, not the inverse. All right. So we can also generalize this power function rule. It is, well, when we multiply this x to the power n with some constant c. What is its derivative? Its derivative is c times small case n times x to the power small case n minus 1, or f prime of x equals equal to c times n times x to the power minus n minus 1. This one. All right. Let's apply it and then let's prove it. In this example, y is equal to 2x, great. And we have dy over dx as 2x is 2x to the power 1. When I put 1 in front, is 2 times 1 is 1. And 1 minus 1 is 0. 2 times x to the power 0. X to the power is 1. 0 is 1. So 2 times 1 is 2, you see. The derivative of y equals 2x is 2. The derivative of f of x equals 4x to the power 3 is easy. It's f prime of x equal to, just put 3 in front of x. 4 times 3 is 12. X to the power 3 minus 1 is 2. 12 times x to the power 2, you see? Very easy. And the derivative of f of x equals 3 times x to the power minus 2. What shall we do? We shall just put minus to front of everything, and front of x. So we obtain 3 times minus 2 is minus 6. X to the power minus 2 minus 1 is minus 3. You see? Minus 6 x to the power minus 3. Very easy to apply. But let's prove it as well. We have proven for the case x to the power small case n, but we haven't proven for c times x to the power small case n. So let's prove it as well. F prime at a point, at a particular point n, without specifying anything about n, any real number, it is equal to limit when x goes to big case n of f of x minus f of n over x minus n. This is the general formula. This is the general definition of a derivative at a point. All right. What is f of x? It is c times x to the power n. What is f of big case n? It is c times big case n to the power small case n. And at the denominator we have x minus n. But can I take c in factor? Yes, I can factorize it. I can take c in front of the expression and write it down as limit x goes to n of c times x to the power n minus n to the power n over x minus n. But I know that from my limit theorems, the limit of a product is the product of the limits, which means the limit of this expression c times x to the power n minus n to the power n over x minus n when x goes to n is the limit of c when x goes to n, big case n, times limit of x to the power small case n minus big case n to the power small case n over x minus n when x goes to the big case n. So this is the product limit theorem. But limit of a constant, c is a constant, limit of a constant is itself, we have proven it as well. So limit of c when x goes to n is c, and we obtain c times limit of, when x goes to n of x to the power n minus n to the power n over x minus n, this one, from limit of a constant. But what is this limit of x to the power small case n minus big case n to the power small case n over x minus n when x goes to n? We have proven that it is equal to small case n times big case n to the power small case n minus 1. And we multiply it by c, we obtain the result we want. This is the proof. But we have to generalize it as well. So no constraint is put on big case n. Thus, this result is valid for all real n values, and that's to say for all real x's, f prime x is equal to c times n times x to the power n minus 1. You see? Quite easy. Alright, here there are some exercises. You just try them, and you have also at the end of the of your book there are some solutions, but I sent you, you will find at the introductory page of our course also some English materials. There you have the book of solutions. You can find the solution of all these exercises in this book as well. So you try first and you look at the results afterwards. And you can always ask me whenever you have something which is not so clear. Great. So now we are at 7.2, the second subtitle of our chapter 7. Rules of differentiation involve two or more functions of the same variable. These are very interesting as well. We have now more than one function. For instance, f of x and g of x, which are continuous and once differentiable functions at least. So you can take they are continuous, and you can take their first derivative at least. This is C1 means continuous and differentiable, once differentiable. What is the sum or difference rule? It is easy. The sum of the derivative of the sum of two functions is the sum of their derivatives. The derivative of the difference of two functions is the difference of their derivatives. This is the rule. You see, it is written here as well. d over dx of f of x plus g of x is d over dx of f of x plus d over dx of g of x, or f prime of x plus g prime of x. For the difference, it's similar as well. The plus sign is replaced by minus. It's the same formula. Let's prove it. For all n in R, which are real numbers, we just invent a function phi n, phi of x. You will see why we do it when we replace it with other functions, with the functions we want. In fact, this is a general function phi of x, and phi prime at the point n, the derivative of this function at the point n, big case n, is limit when delta x goes to 0 of delta phi x over delta x. Or if you wish, it means the derivative of a function is the limit of the rate of change when the delta x goes to 0. Or we can also express it as limit when x goes to big case n of phi of x minus phi of n over x minus n. The formula we know. So phi of x, instead of phi of x, we replace it with f of x plus g of x. If we want to prove for f of x minus g of x, then we will replace phi of x with f of x minus g of x, whatever we want to prove. So phi of x is a general function. It's like a dummy function where we put inside the expression we want to prove. So phi of x is f of x plus g of x. Let's accept it as it is. So the derivative of it, the sum f plus g prime at n, at the point n, is equal to limit when x goes to big case n of f of x plus g of x minus f of n plus g of n. So we replace these phi's by their values. Phi of x is f of x plus g of x. Phi of n is equal to phi of phi of n. So yes, f of n plus g of n. So we obtain limit x goes to n of f of x plus g of x minus, in parentheses, f of n plus g of n, and the whole divided by x minus n. This is our formula, what we obtained so far. So just grouping using the associativity, commutativity, and associativity laws of the or properties of the addition, then I can write this down as when x goes to n of f of x minus f of n plus g of x minus g of n, the whole thing over x minus n. Great. Then I can distribute this denominator in both parts and say this is equal to, and I can distribute the limit inside as well, because the limit of the sum is the sum of the limits, the rule of the limit. So sum of limit of the sum theorem or sum of limit theorem, whatever you wish. This is equal to the limit when x goes to big case n of f of x minus f of n over x minus n plus limit of g of x minus g of n over x minus n. But what is the first part? It is the derivative of f at the point n, and the second part is the derivative of g of n, g of x at this point n. So f prime of n plus g prime of n. So we have proven for a particular point n, but we generalize it since no constraint is put on this particular value of n. Thus the result is valid for all real n values. That's to say, for all x in the real space, f of x plus g of x, derivative of f of x plus g of x is equal to derivative of f of x plus derivative of g of x. F of x plus g of x prime is equal to f prime of x plus g prime of x. So this is the general result. All right. How can we use it? In several ways. One way is this one. For more than one, first we can generalize to more than one function. If we have a function f of x plus g of x plus h of x, the sum of three functions, its derivative will be this sum of the derivatives of each one. So f prime of x plus g prime of x plus h prime of x. If it is fx minus gx minus hx, its derivative will be f prime of x minus g prime of x minus h prime of x, or any combination you can obtain. Various combinations, like f of x plus g of x minus h of x, then its derivative will be f prime of x plus g prime of x minus h prime of x naturally. It is a linear operator. The derivative is a linear operator. All right. The first example goes like this. Y is equal to 14 x to the power 3, 14 times x to the power 3. The derivative of this expression is very easy, of this function. Just put the 3 in front. 3 times 14 is 42. X to the power 3 minus 1, x to the power 2. So it is 42 x to the power 2 x squared. Easy. But if we divide this 14 x to the power 3 as 5x to the power 3 plus 9x to the power 3, if we weren't given 14x to the power 3, but in parts 5 x to the power 3 plus 9x to the power 3. What is its derivative? Then we will take the derivative of each part, which means the derivative of 5x to the power 3 plus the derivative of 9x to the power 3. What is the derivative of 5x to the power 3? Just put 3 in front. 3 times 5, 15x to the power 3 minus 1, 2, 15x squared, plus 3 times 9, which is 27, x to the power 3 minus 1 is x squared. So 15x squared plus 27x squared makes 42x squared, which is equal to the straightforward derivative which we found before. So you can go both ways, you will obtain the same result. Another example, we can divide this 42x to the power 2, or not 42 this time, but 13 plus 2, 15 minus 1, 14. So if we have y equals 2 times x to the power 3 plus 13 times x to the power 3 minus x to the power 3, you see, which means 13 plus 2, 15 minus 1, 14 x to the power 3, the same thing, but divided this way now. It is separated. It is sort of given in another expression. So if we want to take the derivative of 2 times x to the power 3 plus 13 times x to the power 3 minus x to the power 3, you can either make the sum and make 14x to the power 3 and take the derivatives we have done here, or you can take the derivative of each one and then sum up. So 3 in front of the 2x is 6x to the power 2, 3 minus 1, 2. And you just put 3 in front, 3 times 13, 39, x to the power 2, and minus 3 times x to the power 2. So what does it mean? 39 plus 6, 45, minus 3, 42, x to the power 3, 2, which is the same result as before. But this is not so important, so interesting. What is interesting are polynomials, derivatives of polynomials, any polynomial. For instance, if we have a quadratic polynomial such as a times x squared plus b times x plus c, its derivative will be very easily, isn't it, to just put 2 in front of a times x, so 2 times a to the power x to the power 2 minus 1, we reduce it by 1, so x to the power 1, so 2 times ax plus bx, x is to the power 1, when we put with 1 in front is 1 times b times x to the power 0, x to the power 0 is 1, so this is b. And c is constant, its derivative is 0, so we obtain 2ax plus b plus c, which is 2ax plus b. This is the derivative of this expression, you see. And another one is this one. 7x to the power 4 plus 2x to the power 3 minus 3x plus 37. If you take its derivative, quite easy. Well, 7x to the power 4, we just replace 7x to the power 4. We just put, for instance, we will take the derivative of 7 times x to the power 4 plus 2 times x to the power 3 minus 3 times x plus 37, this polynomial. We will take the derivative. How shall we take the derivative? We will take the derivative of each monomial, each part of it, and sum up. Very easy, isn't it? Very easy indeed. All right. So, just using the formula, put the power in front and reduce it by 1. 4 times 7, 28, x to the power 3, plus 6 times x to the power 2, minus 3, plus 37 plus 0, which is 28x to the power 3 plus 6 times x to the power 2 minus 3. You see? So the polynomials are easy to differentiate, to take derivative. An economic example is this one, the total cost function. The total cost function is the total cost of making something, of producing or of selling something, and it is shown by TC or C of Q. It is a function of the quantity produced of this good or this service, whatever. You see? So, and the marginal cost function is the derivative of this total cost function. And total fixed cost is the fixed part, not changing part of non-changing part of the total cost function. Let's say total fixed cost function is 75. All right. So the total cost function goes like this. C is equal to a q cube minus 4 times q squared plus 10 times q plus 75. This is the total cost function. So if we take the derivative of it, we will just take the derivative of each monomial and sum up. So what is it? We use the same formula. We just put the power in front and reduce the power by 1. So we obtain dc over dq, which is the marginal cost function in fact. Derivative of the total cost function is the marginal cost function. So it is 3 times q squared minus 8 times q to the power 1 plus 10 times q to the power 0 plus 0. 75 is constant, so it disappears. The fixed cost function, fixed cost element will have the derivative 0. So we obtain 3 times q squared minus 8 times q plus 10. This is the marginal cost function, which is the derivative of the total cost function. You see? Easy. All right. So we will learn a little bit vocabulary. The primitive function is the function we start with. It can be called the total function as well if it is the total of something. The derivative function is the function we obtain by differentiating, by taking the derivative of it, and in economics it is called marginal function. The smoothness, non-smoothness of a function means whether it has some angles, some corners on the function or not. For instance, this one is a smooth function, this one is not. This one makes a corner here, so it is not. Those are smooth functions. All right. Continuity, discontinuity. Continuity is intuitively to be able to draw a function without taking the hand off the paper, without taking the pen off the paper. This is continuous, this is continuous. This function here, we have a step function which is not continuous. This is continuous, even if it makes an angle, a corner, but this one is not continuous. See, it is in two parts. I cannot draw this function without taking my hand off the paper or the pen out of the paper. So this step function is not continuous. And differentiability, a function is differentiable if we can take its derivative at any point. These functions are differentiable, but this function, when it makes a corner, at the point where it makes a corner, it is not differentiable. We will see why it is so shortly. So the continuous differentiability means a function is continuous and you can take its derivative. It is differentiable. Differentiable means it has a derivative at a given point. So we have a notation here, C0. In fact, this 0 should have been at the superscript. It would be, it's not C of 0, it is C0. There's a small mistake, not a mistake, but a misprint here. C to the power 0 it should be, like the C to the power 1 in parentheses and C to the power 2 in parentheses, which means F is an element of C0, means F is a continuous function, but it's not necessarily differentiable. Its derivative may not exist. C0 is continuous. If F is an element of C to the power 1, it means it is a continuous and once differentiable function. You can take its derivative for once. if we write f is an element of c2, c to the power 2, it means it's a continuous function. Its derivative and the derivative of its derivative, the second derivative, can be taken twice differentiable. And it goes on like this up to infinity. If f is an element of c to the power infinity, which means f is continuous and infinitely differentiable. You can take its derivative, the derivative of its derivative, the derivative of its derivative, etc. You see, it goes on like this up to infinity. So, all right, here we see some examples of total functions or primitive functions and their derivative functions. If y is equal to 1 plus 1/2 of x, this is the total function. Its marginal function, which is its derivative, is 0 plus 1/2, which is 1/2. dy over dx is equal to 1/2. You see, this is y equals 1 plus 1/2 of x, which is this line with a slope of 1/2, and passing when x is 0, it passes by 1. This is the total function or the primitive function. But dy over dx equals 1 over 1/2, which is a constant function passing by 1/2 here, which intercepts y-axis by 1/2. This is its marginal or derivative function. If the primitive or total function is y is equal to 1 or 1/6 of x to the power 3 minus 10 times x plus 50, its derivative is dy over dx. When we put 3 in front, 3 over 6 is 1 over 1/2 x to the power 2 minus 10 times x to the power 0 plus 0, which is 1/2 x squared minus 10. This is the marginal function of this total function, or this is the derivative of this primitive function. You see, if we draw them on the same system of axis, on the same Cartesian coordinate system. You see? So, an example which is more significant, more interesting is this one. Here we have a function consisting of two parts. Y equals 5 minus x for x less than or equal to 3, and y equals x minus 1 for x greater than 3. This is the x equals 3. So we have at the left part of the left side of the tree, we have y equals 5 minus x. When x is 0, it passes by 5. It intercepts the y-axis by 5 at 5, and it has a slope of minus 1. The derivative of this part is minus 1. When x is greater than 3, the value of the function is x minus 1, which is when x is 0, it passes by minus 1, and it goes up with a slope of 1. The derivative of this function is 1. So the derivative of y dy over dx is minus 1 for x less than 3 and 1 plus 1 for x greater than 3. Its derivative consists of two parts. And at x equals 3, it is not defined. Why? Because here we can have tangent lines to this corner, infinitely many tangent lines whose slope would be between minus 1 and 1. It doesn't have one derivative, it has an infinity of derivatives here. So it has no derivative. For x less than 3, its derivative is minus 1, its slope is minus 1, its derivative is minus 1. For x greater than 3, its slope is 1, its derivative is 1. But at the very point x equals 3, the derivative of this function doesn't exist. So in the book there is a mistake here. It puts I think it doesn't put this small half moons. You should put these small half moons, and this should be empty here. You can't put a black dot somewhere because there is no derivative at x equals 3. So it should be shown this way. All right. So Now the product rule. What is the product rule? The derivative of the product of two functions, f of x times g of x. What is the rule? It is, well, here it is expressed a little bit differently, but it's usually expressed as f prime of x times gx plus fx times g prime of x. You see? So the derivative of the first one times the second function, the primitive of the second function, plus the primitive of the first function times the derivative of the second function. And it goes on like this. You can generalize it to many functions as well. At each time, you take the derivative of one and you multiply with the primitives of the others. See? And we will generalize it indeed. So here, in our book, it made like this. Instead of sort of putting things in this order, it puts like the primitive of the first one times the derivative of the second plus the primitive of the second times derivative of the first one, which is the same thing, but the order is reversed. So f of x times g prime of x plus g of x times f prime of x, which is equal to f prime of x times gx plus f of x times g prime of x. It's easier and sort of more intuitive to express it in this way, in the way I wrote. So let's find the derivative of y equals 2x plus 3 times 3x to the power 2, x 3x squared. What shall we do? We shall first take the derivative of this one. There are two parts, two functions. F of x is 2x plus 3. G of x is 3x to the power 2. Great. So what shall we do? We shall take, for instance, here, if we follow the Book's formula, we shall take the first one and multiply it with the derivative of the second one, and then take the derivative of the first one and multiply it with the second one. Or if we apply the general formula f prime of x times gx plus fx plus times g prime of x, we just take the derivative of the first one, which is 2, and multiply it by the second one, 3x squared here, plus the first one, the primitive of the first one, multiplied by the derivative of the second one, which is 6x. So 2x plus 3 times 6 times x plus 3x squared plus times 2, applying Book's formula. Or if you wish, 2 times 3x squared plus 2x plus 3 times 6x. This is this formula. They are the same. And the result, 2 times 6x, 12, 12x squared plus 6x squared, 18x squared, plus 3 times 6 is 18x. So the result is 18x squared plus 18x. But how can we do it without knowing this formula? We can just multiply these two functions and then take the derivative. So 2x plus 3 times 3x squared is, when we multiply, 6x to the power 3 plus 9x to the power 2. When we take its derivative, it is using the power function rule. We just take the power in front and then reduce the power 1. So 3 times 6 is 18, x to the power 3 minus 1, 2. And 2 times 9 is 18, x to the power 2 minus 1 is 1. So x. So 18x squared plus 18x, which is the same as the result we obtained using the product rule. You see? So we can justify our result. We can control our result. We can check our result. So let's prove it. This proof is a little bit delicate. You should be careful about this proof. Why? Because we'll make a trick here. For any real number n, for any n which belongs to the set of real numbers, we just take phi x again as a general function. Phi prime of n is limit when delta x goes to 0 of delta phi x over delta x. This is the definition of the derivative. Alright, at a point. We can express it as limit when x goes to n of phi x minus phi n over x minus n. Phi of x minus phi of n over x minus n. This is the rate of change of the function phi, and when we take the limit of it by when x goes to big case n, we obtain its derivative. So let's replace phi of x by fx times gx in this formula. So the derivative of fx times gx when x is equal to n, which is phi prime of n indeed in this case, is limit when x goes to n of f of x times g of x minus f of n times g of n over x minus n. Great. But this is very good, but it doesn't help me much. I should be able to put some terms in between so that I can obtain two derivatives. What shall I put in between? Well, since I have in hand f of x times g of x and f of n times g of n, I can put f of x times g of n or f of x n times g of x. Cross terms, one of the cross terms. And in order to introduce this cross term between these two, what shall I do? I will just subtract and add this term. This is a common trick used in mathematics to introduce to put some expression which is not there, which I need, without changing the formula. So if I don't want to change the formula of something but add a extra element in this formula, then I can add and subtract this term or multiply and divide by this term. So the formula will not change. Making this, I add and subtract f of x times g of n. What do I obtain? The denominator, the numerator becomes f of x times g of x minus f of x times g of n plus f of x times g of n. You see, I subtract and add the same thing, so it doesn't change. Minus f of n times g of n. And the denominator is x minus n. Great. Very good. So here from the first two terms, I can factorize, and I can take to the factor f of x as a product. So I obtain f of x times g of x minus g of n over x minus n plus, just also distributing the denominator in two parts. Here I have g of n, which is common in the two final terms. I took g of n to the factor, and I obtain g of n times f of x minus f of n over x minus n. Great. So this is the transformed form of this rate of change. When I take the limit of this expression, when x goes to n, I obtain the derivative of the product. So d over, you see, the limit of the sum and the limit of the product theorems. I use the limit of the sum theorem to distribute the limit in those two parts of the plus sign, and I use the product limit theorem in order to distribute the limit in these products. We have two products summed up. So in order to distribute the limit at the two parts of the sum, I use the limit of the sum theorem. And in order to distribute the limit in these products, I use the product limit theorem, so that I obtain limit of f of x when x goes to n times limit of g of x minus g of n over x minus n when x goes to n plus limit of g of n when x goes to n times limit when x goes to n of f of x minus f of n over x minus n. Here we are. So what are these? Limit of f of x when x goes to n is f of n. Limit of g of x minus g of n over x minus n when x goes to n is the derivative of g of x at the point n, so g prime of n, plus limit of g of n is a constant, so it is g of n itself when x goes to n, limit of a constant is itself, times limit of x limit when x goes to n of f of x minus f of n over x minus n. This is the derivative of the function f at the point n, f prime of n. So what I obtain is the derivative of the product f of x g of x at the point n, x equals n. It is f of n times g prime of n plus gn times f prime of n. And since no constraint is put on n, this result would be valid for all real n or all real x's. So fx times g of x accordingly will be f of x times g prime of x plus g of x times f prime of x. But using the commutativity and associativity laws of the multiplication and addition, I can just change the places of these two. I can say f prime of x times gx plus f of x times g prime of x, which is the formula. You can use either this one or this one, but the last one is more common. All right. So for more than two functions, the generalization of this rule for more than two functions, it is easy. It is f of x times g of x times f of h of x, for instance, for three functions multiplying each other. Its derivative would be the derivative of the first one multiplied by the primitives of the second one, the second and the third one, plus the primitives of first and third ones multiplied by the derivative of the second one, plus the primitives of the first and second ones multiplied by the derivative of the third one. You see? So f prime of x times gx, g of x times h of x, plus f of x times g prime of x times h of x, plus f of x times g of x times h prime of x. So at each round, we take the derivative of one of these functions, multiplying each other, and multiply by the primitives of the other ones, and take the sum of these terms. You see? Then we obtain the derivative of the whole product. This is the general rule. How can we prove it? If we have the case with the two functions in hand, it's very easy to generalize it. What shall we do? We shall do this one. We'll just say that phi of x, this general function, is equal to f of x times g of x. So f of x times g of x times h of x, if f of x times g of x is phi of x, then I replace this f of x times g of x by phi of x. This is equal to phi of x times h of x. So what is the derivative of f of x times g of x times h of x? It is the derivative of phi of x times h of x. All right. And I have just proven the derivative of two functions multiplying each other. This is equal to phi prime of x times h of x plus phi of x times h prime of x. I just used the formula. But what is phi prime of x? It is the derivative of f of x times g of x. I know that this is f prime of x times g of x plus f of x times g prime of x. And I will multiply this by h of x. Plus phi of x is f of x times g of x multiplied by h prime of x. What have I obtained now? Just distributing this h of x in the parentheses. F prime x times g of x times h of x plus f of x times g prime of x times h of x plus f of x times g of x times h prime of x, which is the result I claimed. So I have proven the result. How do we use it? We use it, for instance, for finding marginal revenue function from an average revenue function. This is an economic example. Average revenue, which is the inverse demand function, which is equal to the price. Average revenue is the price indeed of something. So average revenue, which is the price, is a function of the quantity. This is the typical inverse demand function we encounter in our economic books, where we put the quantity demanded on the x-axis and the horizontal axis, and the price on the vertical axis. This is this function. It's called average revenue function. Average revenue is the price. All right. Average revenue, which is equal to the, by definition, total revenue divided by the quantity, because average revenue is the total revenue per quantity of goods sold or produced. Well, whenever you produce, you sell as well. So you obtain your revenue by selling something, not just by producing. You just sell it to someone, to some entity, to the state or to a particular person or a particular firm, whatever. So average revenue is total revenue divided by the quantity produced or sold. And total revenue is the quantity produced and sold multiplied by the price, P times Q, and divided by Q. Q simplify, you are left with P. So average revenue is, well, the price of something. The example, a numeric example, is average revenue equals to 15 minus Q, for instance. Or P equals price equals 15 minus Q, if you wish. The total revenue function, when you have in hand the average revenue, you multiply this average revenue by Q, by the quantity produced or sold, then you obtain the total revenue. So if average revenue is f of Q, and you multiply it by Q, you obtain f of Q times Q. This is the total revenue. For instance, if your average revenue is 15 minus Q, this is a numeric example, when you multiply it by Q, you obtain the total revenue. What is it? 15Q minus Q square. And what is the marginal revenue? The marginal revenue, by definition, is the derivative of the total revenue with respect to quantity, dr over dq, or dtr over dq. This is the marginal revenue. The addition, the contribution of the last unit produced and sold to your total revenue. This is the marginal revenue. This is the derivative of the total revenue with respect to the quantity. So dr over dq, or dtr over dq. But what is r or tr? It is f of q times q. So this is a product. So here we can use the derivative of the product formula, the rule we have seen and proven, in order to obtain the marginal revenue. So the derivative of the first one times the second one plus the first one times the derivative of the second one. It started, the book uses the inversely other formula. So it says the first one, f of q, times the derivative of the second one, q. The derivative of q by q with respect to q is 1. So we obtain f of q times 1 plus the second one times the derivative of the first one. Second one is q times f prime of q. All right. So f of q times 1 is f of q, and plus q times f prime of q. This is the marginal revenue function. You see? And f of q is the average revenue function. You see, average revenue. If I put it on the left-hand side, it becomes minus AR. So I obtain MR minus AR, which is marginal revenue minus average revenue. Marginal revenue minus f of q, which is equal to the right-hand side, which is q times f prime of q. You see? Q times f prime of q. And this is the difference of marginal revenue and average revenue. So, and what is f prime of q? It is the derivative of the average revenue with respect to q. So, I can also obtain numerically from this example. Just note that I obtained total revenue as 15q minus q square. The marginal revenue of this function will be its derivative with respect to q, which is 15 minus 2q. So 15 minus q is the average revenue. 15 minus 2q is the marginal revenue. It is their y-intercept is the same. The slope of the marginal revenue is 2 times steeper than that of the average revenue, and it is negative. Both are decreasing. So Q is greater than 0. Q is always positive. The quantity is always positive. We don't have negative apples or pears. So the Q for us is always positive, whether we produce a good or a service. So for the moment being, Q would be some positive quantity. But then f prime of Q can take different signs, different values. Note, if marginal revenue is less than average revenue, MR minus AR will be negative. Q is positive, so in order this product to be negative, f prime of Q must be negative. This is the imperfect competition case. F prime of Q is negative, a downward sloping inverse demand function, average revenue function, means MR minus R negative, MR less than AR. Marginal should be less than the average in order to take the average down, to make the average sloping downwards, a decreasing function. But if MR is equal to AR, if the marginal revenue is equal to average revenue, their difference will be 0. Then Q is definitely positive, so f prime of Q should be 0. And this is the perfect competition case. Can we have f prime of Q greater than 0? Yes, this is possible as well, although not very frequent, but this is possible as well, when marginal revenue is greater than average revenue. This is possible as well. All right. So if we depict these cases, we obtain something like this. There is this drawing, this figure 7.2 at the book, but it's not very obvious. It's not very easy to understand. Let's see these and then explain the other one. So in our numeric case, 15 minus Q, 15 minus 2Q. You see, this is the average revenue, which is 15 minus Q in our case. This is the marginal revenue corresponding to it, which is 15 minus 2Q. Same y-intercept, which is 15, but the slope is 2 times steeper. This is 15 minus Q. This is y, for instance, 15 minus 2Q, just to give an example. The first one, the uppermost, is the average revenue function, which is FQ, which is the inverse demand function. The lowermost is the marginal revenue. In this case, marginal revenue is always under our average revenue. It is less than average revenue, and difference is Q times F prime of Q. You see, this difference is Q times F prime of Q, and it changes at all points. But marginal revenue is always less than the average revenue, so it just urges the average revenue to decrease. When the marginal is less than the average, it diminishes the average. When the marginal is equal to average, the average remains the same, it remains constant. And when the marginal is above the average, as we see here, it just augments the average. It just adds to the average. You see? So here we see the example, the lowermost example is the example of a imperfect competition, of a monopolistic competition case. The one in between is the perfect competition case, where the price, which is average revenue, is equal to marginal revenue. All are equal to f of Q. Marginal is equal to average. The average remains the same. It remains constant. This is the perfect competition case. And here we have all cases. We have marginal revenue greater than average revenue, so it augments the average revenue. We have this point where marginal revenue is equal to average revenue, where the average revenue stays just constant for one instant, and then one moment, and then marginal revenue descends under the average revenue, and it makes average revenue diminish. You see, you can compare this to this example. For instance, if the the mark that the last student gets from an exam is higher than the average of the other students, when you sum up and when you take the average of when you include the mark of this last one to the whole, take the sum of the marks and take the average per person, when the marginal, which is the contribution of the last unit, the last person to the mark, is higher than the previous average, it will augment the average. If it is less than the average, it will diminish the average. And if it is equal to the average, it will not change the average. This is the case actually. Here we have marginal, which is higher than the average, it augments the average. Here at this side, we have marginal, which is less than the average, it diminishes the average, and just at the point of intersection of the marginal and the average, where they are equal, for one moment, the average doesn't change. Here, the average doesn't change at all because marginal is always equal to average, which is the perfect competition case. Here at the book, this figure is not very easy to understand. It's not very clear, but here we have the average return. Here we have the margin or average revenue, and here we have the marginal revenue, and the distance between them is q times f prime of q. It says here n times f prime of n because it measures it at the point n. So this is n times f prime of n, which is q times f prime of q at the point n. And you find the same thing here as well. This is the distance n times f prime of n, or q times f prime of q at the point n. And you find it here. So, and well, you can obtain it as well. This is n times f prime of n by n. Then you obtain the slope of this line, which is the tangent line to the average revenue at the point n, which is the slope of average revenue. When marginal revenue is less than the average revenue, which is always here in this picture, you see this blue line is marginal revenue, this black line is average revenue. Marginal is always less than the average, so the average revenue is decreasing all over its domain of definition. You see? All right. So, what is the division rule? The division rule goes like this. When we have f of x over g of x, of course the denominator not being 0, otherwise it would be undefined, the derivative of f of x over g of x is equal to f prime of x times g of x minus fx times g prime of x over g square of x. So, numerator, the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, the whole over denominator squared. This is the division rule, the formula of the division. When we have a quotient f of x over g of x, a rational function for instance, its derivative with respect to x will be f prime of x times g of x minus fx f of x times g prime of x over g square of x. G square of x is gx square, of course. It's not a composition of the functions, it's the gx times gx. It's the square of the denominator. Let's see some examples. Well, if we have a rational function like 2x minus 3 over x plus 1, its derivative with respect to x would be the derivative of the numerator 2x minus 3, which is 2, minus 0, which is 2, times the denominator 2 times x plus 1, minus the numerator itself 2x minus 3, times the derivative of the denominator, which is 1 plus 0, which is 1. You see? And the whole divided by the denominator square, x plus 1 square. So 2 times x plus 2 minus 2x plus 3. So 2x and minus 2x cancel each other. We are left with 2 plus 3, which is 5. And at the denominator, we have x plus 1 square. We don't have to make anything else, but x should not be equal to minus 1, of course. Otherwise, this expression would be undetermined. It would be undefined. All right. Another example, 5x over x squared plus 1. Great. What is its derivative? The derivative of the numerator, 5x, 5. Its derivative, the derivative of 5x is 5. Times the denominator, x squared plus 1. Minus the numerator itself, 5x, times the derivative of the denominator, which is 2x plus 0, which is 2x. And the whole divided by the square of the denominator, x squared plus 1 to the square, which is 5x squared plus 5 minus 10x squared. 5x squared minus 10x squared is minus 5x squared plus 5. Or we can express it as 5 times 1 minus x squared, 5 minus 5x squared, or minus 5x squared plus 5. Same thing. The whole thing divided by x squared plus 1 to the square. You don't have to develop this one either. You can just leave it like this. And here we don't have an indeterminacy. We don't have a danger of this function being undefined, because in the real numbers x squared cannot be minus 1. So no problem. All right. This is more interesting. If we have ax squared plus b over cx, for instance, how shall we take the derivative of it? The same formula. The derivative of the numerator, 2ax plus 0, b is constant, this derivative is 0, so the derivative of the numerator is 2ax, times the denominator, which is cx, minus numerator itself, ax squared plus b, times the derivative of the denominator, which is c. Alright. The whole thing divided by c times x to the square, which is c squared times x squared, if you wish. Alright. So if we develop 2ax times cx, 2acx squared minus acx squared plus minus bc. So 2ax squared acx squared minus acx squared is 1acx squared minus bc, and taking c in factor, we obtain c times ax squared minus b. Here we have c squared times x squared. This c and one of these c squared, they cancel each other, they simplify each other. We are left with ax squared minus b over cx squared, c times x squared. You see, one of these c squared x squared, one of these c is the simplified with this c at the numerator. So this is the result. Here again, neither c nor x should be 0, of course, because the denominator cannot be 0, otherwise we have an undefined expression. Alright, so let's prove this formula. Again, we will use this general phi x function. The derivative and phi x in this case will be fx over gx. So its derivative, phi prime of n, is the limit of delta x when delta x goes to 0 of delta phi x over delta x, the limit of the rate of variation of this function. And I can write it down as the limit when x goes to n of phi x minus phi n over x minus n. This is the general formula of the derivative. Great. So if I replace phi of x by f of x over g of x, I obtain phi prime of n equal to the derivative of f of x over g of x at the point under the condition that x is equal to n. This is the same thing. What is it? It is limit of x to when x goes to n of f of x over g of x minus f of n over g of n. Phi of x is f of x over g of x. Phi of n is f of n over g of n. And the whole thing divided by x minus n. Great. Here I can take x minus n, the denominator. I can factorize it as 1 over x minus n, and I can put these two f of x over g of x minus f of n minus g of n in the same denominator, and make f of x times g of n minus f of n times g of x over g of x times g of n, putting in the same denominator, and I took 1 over x minus n as a factor. I will take the limit of all these expressions when x goes to n. Great. What is it? It's a product. But before taking the limit of the product, I will make the same trick again, which I used in the previous proof. But this time I have the cross terms, f of x times g of n and f of n times g of x. So what do I need? I need the straight terms, or f of n times g of n or f of x times g of x. Just try, both will suit. You can, here it introduce f of n times g of n, but you can try the same proof with f of x times g of x. It will give the same result, no problem. So I always sort of intrude, I always put inside the term which doesn't exist there, but in order not to change the formula, I have to add and subtract it at the same time. So now I take this denominator gx times g of n, g of x times g of n, outside, like 1 over g of x times g of n. And I put this denominator x minus n here and introduce this f of n times g of n term. I subtract and add it. So I obtain 1 over g of x times g of n times f of x times g of n minus f of n times g of n plus f of n times g of n. You see, I subtract and add the same thing, so it doesn't change the formula, minus f of n times g of x, and the whole over x minus n. Great. And if I take the limit of this product from the product limit theorem, I just distribute the limit in the product, like limit when x goes to n of 1 over g of x times g of n, and I distribute it in two parts. I take here g of n in factor, and here in these two last ones, f of n in factor. So I obtain limit when x goes to n of 1 over g of x times g of n, the whole distributed, the multiplying g of n times f of x minus f of n over x minus n, minus, I took this minus f of n in factor, I obtain g of n, g of x minus g of n over x minus n. If you take f of minus f of n in factor here, you will see that here you are left with g of x and here minus g of n. So g of x minus g of n over x of x minus n. The denominator is the same. Great. So what shall I do? First, I will use the product limit theorem to distribute this limit inside this product. The first one is limit x when x goes to n of 1 over g of x times g of n times limit when x goes to n of the whole square parenthesis, the whole expression here. Then I use the limit of the difference theorem, the sum, limit of the sum or limit of the difference theorem, to distribute this limit in this difference. And then I will use the product limit theorem to distribute it in all the products, you see. So the difference, limit of the difference theorem, I use it to distribute this limit in two parts of the minus sign. So I obtain limit when x goes to n of 1 over g of x times g of n, this which is already there, times how can I say, these accolade or the beautiful parentheses, where limit x goes to, when x goes to n of g of n times f of x minus f of n over x minus n, this part, minus limit when x goes to n of this part, f of n times g of x minus g of n over x minus n. And I use the product limit theorem to distribute further the limit in these products, and I obtain d over dx of f of x over g of x when x is equal to n as limit when x goes to n of 1 over g of x times g of n times the whole thing, the limit of g of n when x goes to n, times limit of f of x minus f of n over x minus n when x goes to n, minus limit of f of n when x goes to n, times limit when x goes to n of g of x minus g of n over x minus n. The whole thing. Great. So, what shall I do? Here I have a limit. Limit of this product is the product of limits. So g of x, limit of g of x is g of n when x goes to n. G of n is already there. So I obtain here 1 over g of n square. There is a small problem here. Somehow this g has disappeared. But here I have g of n square, 1 over g of n square. Limit of this thing is 1 over g of n square. Great. And here I have limit of g of n, which is a constant, which is itself g of n. And limit of f of x minus f of n over x minus n is the derivative of f of x at the point x equals n. So it is f prime of n, you see. Minus limit of f of n when x goes to n is f of n itself. And limit of g of x minus g of n over x minus n when x goes to n is the derivative of g of x at the point n, which is g prime of n. So I obtain g of n times f prime of n minus f of n times g prime of n, the whole over g square of n. You see? So this is the same formula, but only at the point n. But we generalize it. No constraint is put on the value n. Thus, this result is valid for all real n values, which means for all x's in R, fx over gx prime, the derivative of fx over gx, is gx times f prime of x minus fx times g prime of x over g square of x. Or just changing the places, I can say because I can do it thanks to the commutativity and associativity laws of the multiplication. I can just change these two, you say, and the place of these two, and say f prime of x times gx minus fx times g prime of x over g square of x, which is the result I wanted to prove, you see. All right, so I have in hand all these formulae, I can use them. And a last economic example, the relationship between marginal cost and average cost functions. The same as before, but this time with cost functions instead of revenue functions, and with the division formula instead of the product formula, but the logic is the same. So, the total cost function, TC, is equal to C of Q. It is a function of the quantity produced and sold. The average cost function is when we divide the total cost by the quantity, which is the cost per item, per unit of Q. Average cost is CQ over Q by definition. Those are definitions. 3 equal means definition or identity. So what is the slope of the average cost? It is the derivative of the average cost, which is the derivative of CQ over Q. But this is a quotient. This is a division. So I will use the quotient formula, which I have just proven. So what is the formula? The derivative of the numerator by the denominator minus the numerator by the derivative of the denominator. So C prime Q times Q minus CQ times the derivative of Q by Q is 1. The whole thing over the square of the denominator, which is Q square. All right, great. So I can take from here 1 over Q to the factor. I am left with C prime Q. 1Q and Q square here, they simplify each other. Q is always positive, don't forget it. And it's not 0, it's not negative. Q is always positive. So, and I took 1 over Q, one of these Q square, simplify with 1Q. The other Q, I take it outside as 1 over Q, as the factor as 1 over Q. So here I am left with C prime of Q. And here I am left with CQ times 1, which is CQ over Q. You see? 1q is here, 1q is there from q square. So C prime of q is the derivative of the total cost, which is the marginal cost. Great. And CQ over Q is the total cost divided by quantity, which is average cost. What did I obtain? I obtained 1 over Q times marginal cost minus average cost. What is it? It is the slope of the average cost curve. This one, average cost curve. So Q is always positive. It doesn't change the sign. What does it change the sign? It is the difference marginal cost minus average cost. If marginal cost, you see, if marginal, here we have the general rule, the general result, if you wish. The derivative of the average cost, which is the slope of the average cost, is positive if and only if. You can write it down as if, EIFF, or with this double sided arrow, it is the same. It's a logical arrow, this one, arrow of logic. It means if and only if, a double implication. So the slope of the average cost, the derivative of the average, is positive if and only if C prime of Q greater than CQ over Q, if when marginal is greater than average. You see, when marginal is greater than average, average is this one, marginal is this one. When marginal is greater than average, the average augments. The slope is positive. When marginal is less than average, MC minus AC is negative. So is the slope of the average curve. The average curve is average cost curve is diminishing. It is decreasing. When marginal is less than average, it pulls down the average. When marginal is greater than the average, it pulls up the average. And when marginal is equal to average, the average doesn't change. It is the case where MC equals AC, MC minus AC is 0. So the slope of the average cost curve is 0 for one moment, just one moment, where Q equals 6 in this example. In the numeric example, we can have, this is general analysis. Here we have a numeric example. C, total cost, is equal to Q to the power 3 minus 12Q square plus 60Q. There is no fixed cost here. This is a long run total cost function because there is no fixed cost. Great. What is its marginal cost? We take the derivative 3Q square minus 24Q plus 60. This is the derivative of this function according to this power rule we have seen and proved. What is its average? Average cost curve, average cost function. We just divide total cost by Q. We can divide the whole thing by Q. Q3 by Q is Q square minus 12Q plus 60. This is Q square minus 12Q plus 60 is the average cost curve. Here they drew it for us. When Q is 0, they both pass by 60. This is the marginal cost curve, 3Q square minus 24Q plus 60. And the average cost curve is Q square minus 12Q plus 60. They both intercept the y-axis at 60 because when Q is 0, they both pass by 60 and they make this behavior. And they intersect at Q equals 6. You can control it. You can just equate marginal cost and average cost and see that they intersect at Q equals 6. All right. Or you can put 6 to the average cost and marginal cost and see that they both give the value 30, something like 30, or perhaps not exactly 30, but somewhere in between here. Anyway. All right. So, in fact, this is not 30, I guess, but oh yeah, it is easy. When I take the slope of the average cost curve, then I take the derivative of the average cost curve. The slope is the derivative. So when I take the derivative of the average cost curve, it is 2Q minus 12 plus 0. So 2Q minus 12. Where is it 0? It is where 2q minus 12 is 0, where 2q is 12, q is 6, q star is 6. It is the minimum of the average cost curve, where the marginal cost intersects the average cost. You can also see from here. At the chapter 9, we will see it better because we will learn the optimization over there. How to maximize or minimize, find the minimum and maximum of the function. All right. You see, but the general rule that we have proven and we have also seen by examples is that the message of this lesson, when the marginal is less than the average, it pulls down the average. The average diminishes. When the marginal is equal to the average, it doesn't change the average. The average remains fixed for constant for some time. And when the marginal is above the average, when the marginal is greater than the average, it pulls up the average. The average augments. This is value in economics, in physics, whatever you wish. So, and here you have the exercises of these subheadings. So you should try them. You should see the solutions in the solution book. And if you don't understand something, you should ask me. Thank you for today. I will stop the recording.